Hello, everyone. Welcome to our first edition of Physica Live. Today, we're happy to welcome Dr. Alexandra Trettin from the University of Manchester.
She will be talking to us about her research on neutrinos and also other particle physicists, as she's very good at that. That's what her doctorate is in.
Hello. Yeah, thank you for the introduction. And let's get right into it, unless you want to ask me something about myself first before we get started.
So Dr. Trettin in her previous talk just now explained to us that she was born in Germany, close to a small village, and then moved to somewhere in Berlin, close to Elon Musk's gigafactory. And then went to Berlin for her schooling and went to the Humboldt in Berlin.
Mm-hmm. Yes, so I studied physics. I did my undergraduate, bachelor's, and master's degree at the Humboldt-Universität zu Berlin. And I then did my PhD, still staying within Berlin, or rather just outside of Berlin, at the DESY Institute in Trettin, where I did my PhD on IceCube. Which was a search for sterile neutrinos with IceCube deep core.
That's very interesting. So now Riddick is going to introduce us to the standard model.
So essentially, the standard model is an overview of the different particles involved within particle physics. So there are two main types of particles, known as bosons, which have an integer spin and are force carrying, examples such as W plus, W minus, and Z bosons. However, the other particles known as fermions, which have half spin, and they only have matter. There are two types of fermions called baryons and leptons, such as electrons and neutrinos.
Yes, thank you. That's a very good summary. Neutrinos, as you've mentioned, they are fermions, spin half particles, and they come partnered with their respective charged lepton of the same flavor. So for the electron neutrino, we have the electron, and for the mu neutrino, we have the muon, and for the tau neutrino, we have the tau particle, which are all electrically charged and only differ between each other due to their mass.
So when you talk about half spin and fermions, what exactly does that mean in relation to the particles themselves? And how does that lead to the transfer of the energy?
Yeah, so the main difference between spin 1 and spin half particles are between their so-called spin statistics. This comes from the treatment of many particles, actually. So fermions follow a statistical model, when you look at many of them, where it is forbidden for two of them to occupy the same state. And that's why atoms don't just collapse into each other, because the electrons are not allowed to all be in the exact same quantum state. Whereas the force-carrying particles, the spin ones, they follow boson statistics, and that means each state is allowed to be occupied by several particles. So really the difference between them becomes apparent in the statistical treatment of many particles.
Now that we've introduced neutrinos, can you give us a brief overview of where these particles come from?
Yeah, neutrinos come from many different natural sources. They were first proposed to explain the energy spectrum of radioactive beta decay. So radioactive decays produce neutrinos and antineutrinos, but they're also produced in the sun. And in fact, the detection of neutrinos from the sun was what definitely proved that the sun gets its energy from nuclear fusion and not any other process. And finally, neutrinos are also produced whenever really fast particles smash into a target. So cosmic radiation that bombards us on Earth all the time produce neutrinos. And we can also do this artificially with a particle accelerator by just shooting these fast particles into a target. Oh, and of course, anything else in the cosmos where particles exchange really high energies and collide with each other tends to produce a lot of neutrinos, such as when a black hole swallows a star, then the massively accelerating matter will eject neutrinos that we can also observe.
Speaking about observing neutrinos, how was that came up with, and what's the history of the neutrino in general?
Yeah, as I've mentioned, at first the neutrino was a stopgap solution. We needed another particle to be there to explain why beta radiation doesn't have a fixed energy, but rather a continuous energy spectrum, so that it was proposed some particle must take a part of the decay energy with it. It cannot all go into the electron. And the idea to prove that this is really happening was developed in the 50s, where people thought about whether we can invert this process. So when you are working the standard model and you are calculating how particles interact and you draw your Feynman diagram, you might have heard of Feynman diagrams before.
Yeah.
They are a way of doing math with drawings. And one fundamental principle of Feynman diagrams is that you can always change the order, and that same Feynman diagram will still be valid. So what this means is that you can run every reaction in reverse. So if you have a beta decay and it ejects neutrinos, you can also capture a neutrino and an electron into some atom, and that will be the inverse beta decay.
Right.
And that is that was the first way of detecting neutrinos, was the inverse beta decay reaction. It changes the type of atom that you have because one of its nuclei changes. So you can then have a big tank full of some material. It undergoes inverse beta decay, and then you observe this change. There are also some other emissions that are happening because the nucleus is changing its type, but that was the first one. And in the 50s, this was done next to a nuclear reactor, and it proved that neutrinos do indeed come out of that reactor.
So we would love to know about neutrino mixing and how the different flavors of neutrinos affect different things and what they actually are.
Yeah, neutrino mixing refers to the fact that the neutrinos can change what flavor of neutrino they are. And the way that this works is essentially the reaction that produces a neutrino, the flavor state, let's say an electron flavor state, is not a so-called eigenstate of the Schrödinger equation. Now, what does this mean? The Schrödinger equation determines how a particle moves through space. It tells you how a wave packet traverses through space. And an energy eigenstate is sort of like a clean sine wave that travels through space. When I say that the electron neutrino is not in eigenstate, it means it's actually a mixture of different energy eigenstates. So when we are calculating how it propagates through space, we need to take it apart into 3 wave packets of different energies. And these wave packets will travel at different speeds because they have different masses. And then when we detect the neutrino again in a detector, then we have to sort of rotate our perspective back. We have to put those mass eigenstates back together to get a flavor eigenstate.
Yeah.
And when we do that, these wave packets interfere with one another, and they can create a different flavor eigenstate. And that's how the oscillation happens.
Yeah.
And mixing refers to sort of the admixture of to which degree the 3 different mass eigenstates mix into each of the flavor eigenstates.
So Riddick is going to tell us now about the next question.
Okay. So one of the key debates with regards to neutrinos is whether they are their own antiparticle. So there are 2 types of particles. They're called Dirac particles, which have its own distinct antiparticle, or there can be either Majorana particles, which are its own antiparticle, meaning that if 2 particles of the same type collide, they'll annihilate or destroy each other. So can you explain how the seesaw mechanism can be used to maybe explain or discover if neutrinos are their own antiparticle or not?
Yeah, so the Dirac mass term is referring to particles that have both a left-handed and a right-handed state. So they follow the Dirac equation. And all of the particles that we know of so far get their mass via the Higgs mechanism, which creates which works on these left-handed and right-handed spinners. Now, the Majorana mass refers to a way of writing down a mass term without this left-handed and right-handed state. So it only has one state and its inverse, and they are the same thing. For all other particles, this mass term is forbidden, because if you were to write this down, you try to give any other particle, like the electron, a Majorana mass, it would break the symmetries of the standard model that we are required. But because neutrinos only interact with the weak nuclear force, which itself only interacts with the left-handed spinners, this Majorana mass term is mathematically allowed. And if it were allowed, it could lead to a very interesting phenomenon where you have both a Dirac mass term and a Majorana mass term, and both of them would participate in this mixing that we have talked about earlier. So the Majorana mass term would be a fourth mass eigenstate that is also produced. And if that mass eigenstate is really heavy, then the math tells us that this heavy mass eigenstate suppresses the mass of the neutrinos that we observe. And that would be a sort of natural explanation of why the neutrino mass is so much smaller than that of any other particles. So that is why we're motivated to look for it. It is mathematically allowed, and uniquely mathematically allowed only for neutrinos, so that alone is already a good reason to search if that exists. But the other is, it would nicely explain this huge difference in mass between particles.
Great, thank you. Now that we've had a little deep dive into neutrinos, I'd really appreciate it if you could introduce your work within neutrino research, such as your IceCube neutrino detector and also Next 100 detector for double beta decay.
Thank you.
Yes, so my PhD thesis was a search for sterile neutrinos. So there I took data from the low energy part of IceCube. So low energy refers to neutrinos between 5 GeV, a giga electron volt, and 100 giga electron volt, which for anyone else would still be really high energy. But compared to neutrinos coming from out there from the cosmos, which can have ludicrous energies of peta electron volts, that is low. So those neutrinos that I've looked at are produced in the atmosphere of the Earth. We know that those are mostly muon neutrinos, and they change mostly into tau neutrinos as they travel through the Earth. And I have measured this oscillation pattern, so as a function of energy and the distance traveled, the neutrino oscillation probability changes, and using a large data set, in this case of over 100,000 neutrino interactions that we've observed, we can statistically determine parameters of the neutrino mixing. And we can also test if there are any distortions to the oscillation pattern that we would not expect from the three known flavors. So for instance, if neutrinos oscillate away into a sterile neutrino state, which could be this Majorana eigenstate, by the way, then they would just become invisible and disappear, and then we could measure that as a deficit that would otherwise not be explained. That is not something that I've seen. I just saw no evidence of any sterile neutrinos, and I put an upper limit on it. Otherwise, you would certainly have heard about it. So that was my PhD thesis, and now I'm working for the next experiment, which means the experiment that is called next, not just my next experiment. Next looks like a big boiler full of xenon gas. It's located in the Pyrenean Mountains in Spain, and there we are looking for the neutrino-less double beta decay. That is a beta decay of xenon that emits only 2 electrons and no neutrinos at all. And that decay would only be possible if, as you said earlier, the neutrino is its own antiparticle, at least to some degree, so that 2 neutrinos can just annihilate each other. And we have not found it yet, but I've done work on calibrating the detector and its properties.
So, based off your work so far, do you think that we will be able to find something soon? And if so, what would the implications of that be for physics?
I think to get to the level of sensitivity at which point we would really expect to see something in the search for neutrinoless double beta decay will still take a couple of decades. The difficulty is that you need to build a very large detector, but it has to be background free. And by background free, I mean there cannot be even the smallest amount of radioactivity in the detector or it would mess up your signal. It is very, very difficult to build a large device that perfectly cleanly. Like we're talking about, if you transport the gas that you're using in the detector over a tall mountain, you ruined it because the radiation coming from the cosmos will radioactively activate your gas. That is the kind of level of detail that we have to look at when we build these experiments. It's going to take decades. So at the moment, this is still basic research. We are learning how we build these large detectors. And then hopefully in the future, we'll see something.
Yeah, that's really great to hear. The future of physics is bright. But we're going to move on to some questions that have been asked by our students and our head of RS, Mr. Riley. So Riddick is going to start off with that.
The first question is, who has gotten the closest in solving the unified field theory?
I don't think I have an answer to that. There are many people who claim to do that, but I've never heard any one of those actually demonstrating anything provable.
Our next question would be more so about your career and life as a physicist, and that is, what is your favorite category in particle physics and why?
Favorite category. I mean, I might just be slightly biased, but I do think that neutrino physics is the best one. No, but really, neutrinos are amazing because they already prove that there's physics beyond the standard model. Even just the fact that they have a mass is physics beyond the standard model. And I do believe that if truly fundamental new physics is going to be found in the near future, is probably going to come from neutrinos.
So, follow-up question to that. We've been asked what the process of you getting into that research was, and I'd like to add, why did that interest you so much as you were becoming a physicist?
I got into this research, well, first in school I was interested in physics. I went to university, got my degree, and at the time, I really did not know what exactly I wanted to get into. I tried some project where I was working in an optical lab, and I really hated it because an optics lab is a dark place and it makes you depressed. So I asked a friend, is there something that I can do where I do some data analysis and programming? He said, oh, come to IceCube, that's fun. And so I did that, and only after really getting myself into that process and working on their data analysis did I actually learn to really love the field. Yeah, basically, if you want to get into something specific as an undergrad student who is still working on their degree, Shop around, ask professors, hey, you're doing interesting research. Do you have space for a master student? Or look for master classes. That's something that you can even do now in high school. Experiments, like we in Manchester do offer a master class in physics that is related to Atlas, I believe, so to CERN. And that is something that you can get into right away, and then you can already get your name out to some people who might want to work with you later.
You will definitely see one of us here. And in general, your optics lab sounds a bit like a place that will not be named, but that we may or may not currently be in. Onto some more philosophical questions. We've been asked, what are your views on the theories being created today that we don't actually know are true, such as the particle model, and if they exist, as well as your views about human assumptions in the field of science?
Um, yeah, I'm not really into that game of making up too many unprovable things. I do believe that that theories have to make experimentally verifiable predictions, and I myself am not too interested in um, philosophical arguments that don't actually make a difference in the observable world. I just do not see the point. Let's just say.
Fair enough. I think Riddick will explain our next more science-based question.
So thank you.
So this one, yeah, we've done that one. So yeah.
Okay. Our next question is: how do neutrino observations help us learn about distant cosmic events like supernovae or black holes?
Yes, neutrinos are fantastic to look deep into the cosmos because they're not easily absorbed and they're electrically neutral, so they're not influenced by any magnetic fields and such. And so they allow us to look deeply into any phenomenon that ejects high energy particles. So, for instance, if a black hole swallows a star, then we can see that in our telescopes as gamma rays, and then we can search for neutrino coming also from there and learn more about the reaction that happens. We can also look into what's called an active galactic nucleus, that is a black hole in the center of a galaxy swallowing up material, and it can serve as an early warning system for supernovae because neutrinos actually are able to leave an exploding star before the light can leave it, because light is absorbed. The neutrinos just pass out.
So I think our next big question would be: do you think the standard model is incomplete because of neutrino mass, or are we missing something deeper?
Yes, so the standard model is certainly incomplete, not just because of neutrino masses. So yes, in the standard model, the prediction for neutrino masses would be that they're massless. We know they're not. We are probably missing something that explains how neutrino masses are formed. Of course, also the standard model is already incomplete because it's incompatible with gravity. We know that. So we do expect that we would have to look for phenomena at much higher energy than what we're currently capable of to really put together a better theory of.
And now from our final question, this is the one from Mr. Riley. Is the Big Bang Theory becoming challenged by the latest understandings of physics? I thought there was more to that question.
Well, I do not know how the TV show is being challenged by understanding of physics. But I do not believe that any observations are actually challenging the basic fact that the universe once was all clumped together into a very small point. But exactly how that happened is certainly something that is being challenged. Though mostly that is happening through cosmological observations. So, for instance, the recently launched WST Space Telescope, James Webb Space Telescope has caused tensions between different ways of measuring the expansion of the universe, and that is certainly challenging our models of how general relativity works, how dark matter works, and with that, how the early universe must have formed.
Yeah. So Riddick is gonna end us off here.
Excellent. Thank you. Unfortunately, we're out of time for today. We'd like to thank Dr. Trettin again for taking the time to discuss particle physics with us.
Yes, thank you a lot for coming all this way, and it's been really great listening to you speak and very interesting.
You're very welcome.
Arjun, Raf?
Yeah, it's great.